Okay, now I want to talk about what happens if we have more than one ODE at a time. Okay, if we have more than one ODE at a time and they don't link to each other, we can solve them separately, then we really just have a list of first order single one-dimensional ODEs. And that's not what I mean. What I mean is when we have two ODEs that are coupled. Let's take a look at what that looks like. So if, and actually let me make this a different function. If we have an x dot equation, so for one variable named x dot, and we have a y dot equation for a second variable named y dot, they are just going to be functions of x dot, of x, and so on. But coupled means that y appears in the x dot equation and x appears in the y dot equation. It doesn't have to be both, it could just be one way, but still that means they're coupled. That means that I can't find a solution for y without knowing something about x, and I can't find a solution for x without knowing something about y. Let's think of a really simple example to get started. We had the Brunt-Weisela equation, which we solved as a simple equation a few chapters back. And it has this nice form where we think this is where we take a water mass and displace it in stratification, and it bounces up and down. So this is the displacement distance, this delta z, and there's an n squared here, which is a constant, the Brunt-Weisela frequency. Okay, well you might say, wait, you're cheating. That's not two coupled ODEs, two coupled first order ODEs. That's a second order ODE. But I can play a very simple game and call x delta x and call, delta z, and call y delta z dot. Let's see what happens if we plug that in. Okay, so d dt of delta z, I could say that that was either the second derivative of x, or I could say that that was the first derivative of y. So let's write it as y dot equals minus n squared x. Okay, that's great, cool. That's definitely a coupled equation between x and y. First order. Where's our second equation though? We need an equation for x dot in terms of y. Well, look back here at our definition. That actually says y is equal to z dot, which is just equal to x dot. So our second equation is x dot is equal to y. And this is the kind of equation you frequently get when you have a acceleration, which is a function of position. So acceleration, position, what we're doing here with y is we're actually introducing the velocity. Y here is the velocity, and this, so the time derivative of the velocity is the acceleration, and the position x is both the position, but it's also related to the velocity by this simple differentiation rule. Okay, so that's how we get these equations. How do we solve them? Well, I've just rewritten it up here. We can do this a lot of different ways, but one of the most interesting ways to do it is to take the time derivative over here as a linear operator. Multiplying by these constant coefficients over here is also a linear operator. I could write this as a matrix equation. I could take d dt x and y, so that just means take the time derivative of the upper component, take the time derivative of the lower component, the two equations, and that'll be equal to some kind of matrix times x and y. Well, let's see, what is it? In the x equation, I need y, so that's 0 and 1. And in the y equation, I need minus n squared times x, minus n squared, 0. All right. what would be really nice is if we could write this separately as an equation for something that's like, if we could separate out the x part from the y part, and we could pull them apart. We actually can, in general, for this kind of system. We can diagonalize this matrix by looking at its eigenvalues and eigenvectors. Let me write that out. Be right back. Okay, this is how it goes with the eigenvalues and eigenvectors. Well, if I knew the eigenvalues and eigenvectors, I could diagonalize this matrix, M, and write it as C, which is the set of eigenvectors, a diagonal matrix with the eigenvalues in it, and the inverse of C, which is the constructed from the eigenvectors as well. And all of this is laid out in our linear algebra chapter. You don't have to do these calculations for any matrix. You can just write this down from those solutions. Cool. Okay, so let's see what happens if we plug that into the differential equation. Well, we're just replacing the matrix now with C dC inverse. And we can move this C over to the other side of the equation, and since it's just a mess of constants, we can pull it inside of the differentiation. It doesn't make any difference. So now we have d dt of C inverse times xy equals a diagonal matrix, lambda 1, lambda 2, times C inverse of xy. Well, look, C inverse acting on x and y, this is just a new way of writing the unknown, and it's the same on both sides of the equation. And in fact, whatever the first row of C inverse acting on xy is, that will be equal to itself times the first eigenvector. Wait a minute, that means that we, not the first row, the first column will be equal to itself, the first column will be equal to itself times the first eigenvector. So what that means is that we have a new solution, which is whatever the first column is of C inverse acting on x and y is a new variable, and it participates in an uncoupled equation from the second column, which is acting on the second eigenvector, our second eigenvalue, and the second eigenvector. So the cool thing about it is, in general, we can decouple these systems just by using the eigenvectors and eigenvalues like this. Once we've decoupled them, we can go on and do our regular old, hey, look, this is homogeneous. We could do our regular old guess and check from there. More generally, we might have ended up like something like this, where we had fixed points, and this was a linearization of a 2D system around a fixed point in 2 dimensions. And then we might have the same x minus x star, y minus y star, expressing the coordinates of that. And this matrix would be the result of linearizing near that fixed point. We'll get to that in a second. But we're not really interested in solving the ODEs or even the coupled ODEs right now, so much as we are understanding the behavior of different parts of phase space. And in this case, the phase space has just gone up in dimensionality. So we can't draw a 2D plot which has x and x dot and y dot. We're going to have to somehow signify x dot and y dot as well as x and y all at the same time. So in the 2D problem phase space, you tend to draw x and y, locate the fixed points or other characteristics of that behavior, and then draw arrows to indicate the direction of flow. Arrows, just vectors, like x dot and y dot throughout the space. So let's go ahead and do it for this case. Whoop, whoop. Here's x, here's y. All right, what can we do? Well, all right. This is a homogeneous system. If I set both x and y equal to 0, then x dot and y dot are also equal to 0. So I actually have a fixed point at x equals y equals 0. Cool. What happens if I go to positive x but keep y equal to 0? Positive x here, hey, that is going to be non-zero. There'll be a minus n squared in the y dot direction. Boop. But y is equal to 0, so there's no x dot. So that means I'll be going down here. And if I go farther out, I have a constant coefficient, but I'd be going down faster. What about if I go to negative x's? I'd be going up. I'd be going up faster. Down and up, just like that. Okay, that gives us a sense of what happens on the x-axis. What happens if I go up and down on the y-axis? Well, if I go up on the y-axis, my x dot is just equal to y, so it's positive, and it's more positive up here. It's negative. It's more negative down here. If I go diagonally out, I'm actually going to find connecting values like this in between. In fact, if I forget about the n squared factor, I can see that these will be circular orbits, or I guess they'll be elliptical orbits, including the n squared factor, going around in this direction. And so we have a fixed point in the middle, but around it we have these stable orbits. So we have a new characteristic. It's not a fixed point. It's not steady in time, but it's repeating in time. It's going around and around and repeating in time. So fixed orbits like this is one of the characteristics of a linear second-order differential equation that doesn't occur in a first-order differential equation. And you might have seen this, depending on how it was taught to you before, that in first-order differential equations, all you can do is just either fall into a hole or run away from the fixed point. There's just two solutions: exponential growth, exponential decay. Second-order differential equations, or in two coupled first-order ODEs, which, as we just saw, are the same thing once you introduce the velocity variable, you can have oscillations. Cool. But oscillations are the only things you can have. What if we added another minus factor here on the other side? If this was 0, I wouldn't do anything, but if these terms are there, and they could even have a small coefficient, that's right, small coefficient, and let's make it sensible units. So let's give it time units, tau. So tau could be a very, very small, a very, very large number, which means that the time scale is very, very large for this behavior, whatever it is. Neglect these for a second, and you see that what we have is x dot just decays down to 0 with this time scale tau. Y dot just decays down to 0 with this time scale tau. So we put together the oscillation and decaying. What do we get? We're going to get inward spirals. So we still have that same fixed point at the origin, and now, even though we might start out on those oscillations, they're going to damp and go into the root. So inward spirals, or I could flip the sign here, outward spirals are going to be other characteristics of the 2D phase space. And I guess I should say, the other one you might have is, if we didn't have the oscillation at all, we could just have everywhere collapsing into the origin without the oscillation. So we're going to have a complete fall in from all directions. Probably might occur to you? Well, anyway, if we take the matrix approach that we started out on and we plug it into the eigenvalue calculator, and we get two eigenvalues out, we could sum those eigenvalues, get a number. We could take the determinant, which is the product of those eigenvalues, we get a different number. Those two numbers would characterize the behavior in this kind of phase space. If they were both negative and real, we tend to be moving towards the origin. If they have an imaginary component, we tend to be oscillating around. If they were positive, we'd be heading out. And so it turns out there's a limited number of behaviors you could have. And so on this page in the notes, those different behaviors are laid out. So here on this regime diagram in the bottom, you can see that as you vary the trace, which is the sum of the eigenvalues, or the determinant, which is the product of the eigenvalues, from positive to negative, you can get all different kinds of behaviors. These are the kinds of flow patterns that you'd expect. The eigenvalues are not obviously related to this, and in fact, along with the eigenvalues here, the eigenvectors could be in lots of different orientations, which could make these look very different. Might be hard to graph them all, but you could do it. And then down here, so if you're in this regime, you have unstable spirals. In this regime, you have stable spirals. You can have unstable node, a stable node, which is just falling inward to it. You could have a center, which looks like this, where it's got oscillations all around it without spiraling inward or spiraling outward. Or you could have saddle points, which is where you're coming in one direction and going out in the other. It's sort of the 2D equivalent of the half-stable solutions in 1D.